Thank you, Sasha. It's a pleasure to be here. I'm not going to talk about machine learning. I'm not going to talk about deep learning. I'm going to talk about what's wrong with these approaches and what the alternatives that we suggest. So the title of the talk is Autonomous Driving from a Science Project to Mass Production. So the thing is that nowadays, autonomous driving, you see many of them around, I think even in Boston, but certainly if you're in the Silicon Valley. But it's currently still a science project. And the question is, what should happen so that these amazing things will be something that we will all be able to afford. We will go to a car dealer, we will buy a car, and they will ask us if we want to pay a little bit more and get the car to be able to drive itself, and we will say, yeah, why not? And we will be able to afford it. So what are the obstacles? So I think that there are two major things which makes it a science project and not a real product. The first thing is safety guarantees. Some of you were probably aware of a recent accident that were involved self-driving cars. We should really define in a rigorous or formal way what are the minimal requirements that every autonomous vehicle must satisfy. What makes an autonomous vehicle safe? What does it really mean to be safe? And how to ensure safety when we have uncertainty, we're not sure about what's going on around us. How can we validate that an autonomous car is safe? Is it based on mileage driven? How much data is needed? All these questions need to be answered in a very clear way. The second thing is scalability. So many of the companies that build self-driving cars nowadays, the state of mind is that let's first solve the problem. The cost doesn't matter. Let's be the first to have a self-driving car on the road that is really functioning. So we can throw on it everything, and later we will figure out how to reduce costs. But this later can take a lot of time, because if you from day one don't care about costs, then you will end up with maybe something that is working, but it's not affordable. So it will not be suited for mass production. So the questions are, what is a sufficient sensor configuration? How much computation power do we need? How to scale high definition maps? And another important issue is you cannot build a car which will be very defensive, because it's good for a science project. It's good when there is one car on the road. But if there will be hundreds or thousands in some area, and they will all be very, very defensive, then they will block the city. So if we want to scale up self-driving cars, they should behave like human drivers. Okay? So these are the two issues that I'm going to talk about. These, in my view, are the major things that prevent us from going from a science project to mass production. And I will show you a little bit about what we are doing and what is our approach for tackling these problems. So let me just show you a little bit some videos of driving next to Mobileye offices in Jerusalem. These are human drivers, and it shows why driving is a difficult task. there is a merge here and some poor guy trying to merge into the lane, and nobody really is going to let him do this, okay? It's actually very, very tough. So he gave up, okay? Now look at this truck. It also needs to merge into traffic. And the thing is that it's not California, it's Jerusalem, okay? So people are not that kind. You need to fight for merging into traffic, okay? It's really tough. Not an easy task. You need to negotiate with other drivers and to push your way to the right place. This is a roundabout which is common in Israel and in Europe. Look at these two guys. One wants to go right, one wants to go left. You need to figure out how to do this. Okay. So again, there is a lot of negotiation between drivers. So it's not a trivial thing. A major theme is to balance usefulness and safety. So we can make the autonomous vehicle very safe by making it extremely defensive. So you can avoid any complicated scenario. But the price for this is being useless, because if you will give up, like these poor drivers that you saw before, if you will give up all the time, then you will not reach your destination. Okay, you might also block the traffic of the road, and it's actually might even be dangerous because you might confuse other drivers. So our approach is to build an assertive autonomous vehicle, an Israeli autonomous vehicle, if you want. You want to maintain traffic flow, but on the other hand, you want to be safe. So balancing these two things is a challenging task. Okay, so the talk will be around first safety. What can we do in order to ensure that our cars are safe, and in what sense they are safe? And second, about economic scalability, what are the design choices and the choice of algorithms that allows us to have a solution that each one of you can go to a car dealer and purchase this solution. Okay, so safety. The first thing to notice about safety is that absolute safety is impossible. Okay, what do I mean by that? Suppose that this yellow car in the middle is a self-driving car, and this is a typical highway situation, 3 lanes, you are in the middle. Then one of the drivers on the right lane move into your lane, cut into your lane. There is nothing you can do in order to prevent an accident in this scenario. Okay? So saying that we want self-driving cars to be completely safe and not to be involved in accidents, well, we can say it, but it's impossible. Okay? So if we cannot say that self-driving cars will not be involved in accidents, what can we say? What does it mean to be safe? So one approach which became very popular is what I call the end-to-end statistical approach to safety. The idea is that all this system is a black box, and we need to validate what is the probability that this black box will be involved in an accident. So we want them to be better than a human driver, so we can count the number of mileage driven by a self-driving car, have the statistics of how many accidents there were, compare it to the statistics of a human driver, and say that we are a little bit more or the same ballpark of a human driver, and we are happy, and everything is fine and nice. There are 2 problems with this approach. The first problem is that we believe that this approach, if you do it correctly, is infeasible. So if you manage to do it feasible, you probably do it incorrectly, in other words. Okay? Why? So basic fact in statistics, if you want to make sure that the probability of an accident per hour is at most p, then in order to validate this claim, you need to see 1 over p hours. Okay? At least 1 over p hours. Actually more than that, but at least 1 over p hours. Okay? Because otherwise it is likely that you will not see any event, so you cannot know what's the probability of an accident. But you need to see 1 over p hours after every update of the software, because it's an end-to-end validation. So if you change even something small in your software, maybe it has some butterfly effect and it creates a new accident that you didn't think about it. You're not arguing anything about the system, but refer to it as a black box. Okay? Now, if you think about what should be p, so the statistics for human driver is roughly p equals to 10 to the minus 6. So you need million of hours after every update of the software. This is pretty crazy. Okay? Now, a possible solution is to rely on simulators. But simulators have exactly the same problem, because you can check your software on a simulator, but who says that the simulator reflects reality? So you need to validate the simulator, and then this is basically the same problem. Okay? And again, even if you validated the simulator on one version of your software, once you change the version of your software, maybe now the simulator is not reflecting reality with respect to the new software. So basically the same lower bound applied. So this is one problem with the statistical approach. Another problem with the statistical approach is that it's not transparent. So say that we could validate and indeed show that self-driving cars makes the same number of accidents per hour, the same probability like a human driver. But the type of accidents might be completely different. So maybe the self-driving car never caused accidents of being distracted by their cell phone. Okay? But they consistently, in some situation, drive over a little kid and kill it. Okay? Will society be happy with such a thing? It's at the same ballpark as human if you count number of mistakes, but these type of mistakes are radically different. Okay? I don't believe that society will tolerate such a product. So the statistical approach is not very good. An even worse approach is what the industry calls the best practice argument. The best practice argument means that a company says that I did what all other players did and more. Of course, here at MIT, I don't need to explain why this is a horrible idea. Okay, so let's move to our approach. So first, we do not believe in black box. We need to break the problem into pieces, okay? And we follow the standard sense, plan, act methodology of robotics. I will explain later. We build a true redundancy for guaranteeing a negligible amount of safety critical mistakes for the sensing part, okay? And by saying negligible, I usually mean roughly 10 to the minus 9. 10 to the minus 9 is 3 orders better than humans and is a standard for aviation. So if you go over a plane, the probability that the wing of the plane will detach is roughly 10 to the minus 9. Okay, so good luck to all who plan to go on a plane today. Okay, so this is for the sensing part. For the planning part, we build a model-based approach, and I will explain later. And for the acting part, we rely on control theory to make sure that the approach is robust. I will not talk about the control part today. I will talk about the sensing part and the planning part. Okay, so visually, we have a system, a sensing system that has a 360 degrees views of what is surrounding the car. as well as a map. And this builds what we call a sensing state. This is a description of the present, description of where you are on the road and where are all other agents around you. Then comes the decision-making part, which we call planning or driving policy. This part is responsible of deciding what to do next. And last, you have the acting part. So you decide that you want to drive like this. Now you need to step on the pedals and move the steering wheel accordingly so that you will drive like this. So this is the acting part. As I said before, I will not talk about the acting part today. All right. So let's start with the sensing part, understanding the surrounding. The goal is to have negligible amount of safety-critic sensing mistakes. And as I said before, this is lower than 10 to the minus 9 probability of an accident or of an event per hour. What are the challenges? So I promised to talk about why machine learning is not good. Here is a first place where machine learning is not good. Machine learning is very good for typical things, for the expected behavior. It's not very good for rare cases, for corner cases. I don't think that any of you ever trained the machine learning algorithm and got accuracy of errors smaller than 10 to the minus 9. Okay? Just for validating this algorithm, you need more than 10 to the 9 examples. Okay? Now, just to appreciate what does it mean 10 to the 9 hours of data, this is the number of hours 1.3 million Americans spend on the road in 1 year. Okay? It's quite a lot.
Is it a subset of 1.3 million, or it's a random
No.
subset of 1.3?
Random subset of 1.3 million. Yeah. All right. Apply some concentration inequality and use. Okay. So how can you rely on machine learning and get 10 to the minus 9 performance guarantee? So the idea is very, very simple. Say you build 3 independent systems. Okay. By independent, I mean that the probability of error for each one of the systems is roughly independent. Now, if each of one is, the failing probability of each of one is at most p, then if you took the majority vote among the 3 systems, then the probability of failure is now only 6 times p squared. Okay? This means that if we want 10 to the minus 9, now we only need roughly 200,000 hours of validation instead of 1 billion. Okay, 2,000 hundreds of hours is something very reasonable to obtain. At Mobileye, we have something like that in our data set. Okay, and you can even further decrease this number by making better voting rules and more roughly independent systems. But the idea is basically the same. Okay, so it's a very, very simple idea. By the way, this is what works in practice, simple ideas. Complicated things usually don't work. So it's a general theme to keep in mind when working with machine learning. If you want highly accurate solutions, just build independent systems, validate individually each system, and then take some simple rules to combine them. Yes.
So I must have missed this part. What is the source of randomness here? Is it the environment, or is it the internal to the system?
The source of randomness is the environment, the world.
So what does it mean to have 3 independent systems that just run on different?
So say one of them is based on cameras, one of them is based on radar, different algorithms, different sensors. So the probability of an error is independent. Yeah?
To enforce that?
Yeah, that's a good question. Can we enforce that? The truth is no. We cannot. Or maybe a better question, how you validate that they are independent. to validate that they are independent, you need 10 to the 9 hours. No, this is a model. And the same thing happens in aviation. How you validate that the wing of the airplane will not fall, okay? You do not fly the airplane 10 to the 9 hours to check this out, okay? You build a model. And here again, it's a model. So you are saying it's assumption. You are saying that one system is based on cameras and with certain algorithms, another one is based on radars and other algorithms. Then I believe that they are at least approximately independent. And I take this belief as something that, that is used in order to proceed. It's a very, very good point.
Are you going to use different trajectories, for instance? Because if you're using the same trajectories for all the systems, they will be dependent on those. You can't have
Here it's not trajectories. Here it's just understanding the surrounding. It's about sensing. It's not about planning.
If I see a spike in some visual system and in some radar system, you know, maybe it's because there were 100 kids that suddenly crossed the roads, right? So in a way, if I see a gigantic spike and like one of the system goes nuts, I can probably guess that the other system is going to go nuts because of this. And this because it's triggered by the same source of the environment. So
But then it's not an error. What we analyze here is what is a probability. What's independent is a probability to make an error. An error is either false positive or false negative. So an error is that you said that there is something there which is safety critical and I must brake very hard on it, but there isn't. This is one type of error. Or there is something there that you must brake on it and you didn't. Okay? This is an event that we say that the probability of this event is independent for the different systems. Because radar are confused by some things, and cameras are confused by different things, and LiDAR is confused by yet another things.
But if the thing is outside of your training set for all methods, then they will be correlated with that.
The things that are completely out of, not necessarily. This is the issue of generalization. So you can argue that if I sample the word IID or in some independent way, and I validated the system on it, then it will generalize to the entire word. Of course, there are errors, but I can give an upper bound on these errors. Okay, this is exactly what all the statistics tells us. All right. Okay, so this is about the sensing systems. So the approach is really very, very simple. Now, I will show you some videos demonstrating our system later, but I would like to emphasize one point. How can you really know that you have 3 independent systems? Okay, it's very easy to cheat yourself. Okay. So our approach is, I want you to drive the car solely based on cameras, drive the car solely based on radars, drive the car solely based on LiDARs, okay? If I can show you that I really have a product based on each sensor individually, then I will believe myself that I have true redundancy. If the things are combined at some stage before then, there is a danger that we cut corners. Okay, so just here is a visualization of our current car. It contains only cameras, 12 cameras that you can see what they see. So there is 3 cameras in the front. One is wide, one is main, and another one is narrow that sees for far distances. There are cameras that look at the front sides, at the rear sides, and there are also parking cameras that looks at the close range around the car. Okay. All right. Okay, so this is about safety of the sensing system. The more challenging thing is safety of the decision-making process. And here we think that the statistical approach is simply the wrong approach. Why? So first, online versus offline validation. For the sensing system, you can collect data once and then validate several systems based on the same data. You just need to be careful, like always in machine learning, to apply the union bound correctly. But apart from this, you can have one big data set and validate several versions of the software on this same data. In contrast, for the decision-making process, what you want to validate is how you interact with other agents. So you must validate it in an online manner while driving. And then it's become impossible to collect data and check a new version. You need to simply drive again many hours, which makes it impossible. Okay? So saying something statistical is just, it's infeasible. The other thing is that in the sensing system, we can strive to have a system that achieves a very high accuracy, something like 1 minus 10 to the minus 9. In the planning part, in the decision-making part, this is simply impossible because of the reason I showed in the beginning. There are mistakes of other drivers, and they count. So you cannot strive at all to have 10 to the minus 9 because it's impossible. Okay? So we must redefine the goal. What does it mean to be safe with respect to the decision-making process? And our approach is to depart from the statistical approach completely and instead redefine the goal. We want that self-driving cars should never be responsible for accidents. And what does it mean? It means that they should never cause accidents. Okay? So you don't want to be the cause of an accident. And if someone else is doing something stupid, you want to respond in a proper way to mistakes of other agents on the road. Okay? So this is a different approach than just counting the number of accidents. We want to minimize or to eliminate completely some types of accidents. These accidents that you cause or that you could have prevented, or even if you couldn't have prevented, you want at least to say that you responded properly to the situation. Maybe there was nothing you could do. Okay? So for this, we propose a model which we call RSS. It's an acronym for Responsibility Sensitive Safety. And this is a mathematical, very simple and interpretable model that aims at formalizing common sense concepts like what is a dangerous situation, what is a proper response to a dangerous situation, and as a result, who is responsible for an accident. And the idea is that we would like to set the rules of the games in advance and not after an accident will happen, because accidents will happen. This is a fact. Okay? And we want in advance to say, okay, for this accident, agent A was doing fine. It's not his responsible. For another accident, agent B was doing fine. Okay? And we would like to set these rules in advance. So what we did is we formalized 4 rules. And we believe that these rules cover most of the bad scenarios that can happen. They are common sense. We can communicate these rules to the wider society and explain this is what the car is doing. Okay? And this is a common sense of the cars. Everything here is very interpretable. And then if an accident occurs, we can show the facts, show a video showing what happened just before the accident, translate it to the language of these rules, and explain why the cars reacted according to the rules. Okay? Now, if the rules are not good, then now it's the time to say that something is wrong with these rules. If these rules are acceptable, then even after an accident, we have a very transparent way to explain what happened. We do not need investigation. We want to be completely transparent in advance.
Do common sense rules and legal rules for determining responsibility, do they always align?
So the legal rules for determining responsibility are fuzzy. In general, we are aligned with the law, but the law misses two things. First, it is fuzzy. It's not backed up by quantitative things. And second, the law is not always about what to do in an emergency. So I'm not familiar with a law that tells you what to do if there is a dangerous situation and you can cross a solid line. Should you do this or not? Okay. I don't know. I'm not an expert in law, but what I'm saying is that so the law tells you that you shouldn't violate red light. Okay, that's for sure. And of course, we're not going to violate red light. But sometimes someone else will violate red light, and you have the green light. You should stop, right? This is not the law. This is common sense. So we are aiming at formalizing common sense more than formalizing the law, because figuring out the law is the easy part. Yeah?
Does it also include vehicle to pedestrian?
Yes, of course.
So I can ask you two questions. So the rule that you wrote there, that kind of fuzzy, so how do you map the notions that you have there to the state space of the vehicle or the environment? Because, for instance, limited visibility can be interpreted in multiple.
I will give examples and explain. Everything is formalized to a very by the way, this is published. You can find papers that describe this model with all the mathematical proofs and all the definitions.
So I'm guessing, here you give us 4 rules, and I'm pretty sure everybody can agree that those are important, but how do I know that those are the only ones? I mean, like, is there a fifth that you decided was actually probably just only 25% important and what making your problem exponentially more complicated?
Put it in the logic formalism, you are asking about completeness of the model.
Yeah?
Yeah, I will talk about it in a minute. Okay.
The other thing is that I was wondering is your goal here? So there's 2 goals to have. One is to be a good citizen, and the other one is to always be on the good side of the insurance company. Is that going to put you always on the good side of the insurance company? I mean, it's sort of linked to the legal part, but there's probably a bunch of accident reports that you guys can just go through and see what makes those things okay.
Which is related to the question of completeness. This is exactly what we did. We went over a data set of 6 million accidents to validate that these rules indeed cover what we want them to cover. So there is a data set of NHTSA, the safety organization, the American Safety Organization. And what we try to do is indeed to check that these rules indeed cover, if not everything, but they cover the majority or very, very large portion of real accidents.
And how about the non-accidents?
What do you mean by the
Well,
non-accident?
there's a lot of rules. There's probably a lot of accidents that are avoided by tacit rules, like crossing a line or something like this. Do you think this is going to have a...
So not crossing a line, I mean, these are the easy part. Saying that autonomous vehicle will not cross a solid line, this is easy to program. This is not the difficult part. Obeying the traffic law, like not violating red light or not going over a solid line, this is the easy part. The hard part is the negotiation with other drivers. When someone else performs something which is a mistake, how you respond. Or when you want to change lane, how you do it assertive enough but not causing an accident. What does it mean? Okay? So let me briefly go over the rules. So the first rule is that if someone hits you from behind, it's not your fault, which is a common sense rule. The second rule says that the first rule is not always true, because if you cut into some other car lane and you are too close and then it hits you from behind, then it is your fault. So cutting we should define what is a good cut-in or a safe cut-in and what is a non-safe cut-in, and we should put the line, okay? The third rule is about right-of-way. Basically, it tells you that right-of-way is given or taken. It means that you can drive normally when you have the right-of-way, unless someone violated the right-of-way. And then if you can stop in time and not hit him, of course, you must do this. Okay? So you should not worry that someone will violate the right-of-way. Hence, when you are, say, driving in green light, you should not worry that some pedestrian that stands and has a red light will jump suddenly into your lane. But if pedestrian violated his red light and started walking and you are at a far enough distance and you can stop in time, of course you must do this. Okay? And the fourth rule is about limited visibility. And here there is a very, very delicate thing, because according to our analysis, people are not very cautious about occluded areas. And we need to set the bar. What does it mean to be cautious enough? Okay. Okay. So now a little bit about formal models in general. There are two things that we should ask ourselves about a good formal model. The first one is soundness. Soundness means that if the model says that you are not responsible for an accident, and I will ask you about the same scenario, you will agree. Okay? And this also a question about completeness that Philippe asked before. So if your model ignoring some scenario because we didn't take it into account, and in this scenario the output of the model is not compatible with common sense of human judgment, then there is a problem with the soundness of the model. The other side is usefulness. You can take all the blame, all the responsibility for all accidents. You will be sound, but you will not be useful. So we also want the model to be useful and to enable a normal flow of traffic. And there is a clear trade-off between soundness and usefulness. This is why we need to communicate with the society through regulators exactly where to put the bar. Because one good example is when you are driving in a residential area and there might be kids that are occluded behind parking cars. Okay? We all, as humans, take a risk. And we drive there, say at 20 miles per hour. Okay? It's not very fast. But if you will analyze what will happen if there is a kid there and he will jump, he might jump to the road, in this scenario you probably will hit him. Okay? So is it acceptable? What exactly is acceptable? So we propose something in the paper. I will not go into the details due to the lack of time. But these are questions that should be answered now and not at the aftermath after an accident will occur. Okay. Regarding usefulness. So suppose that you will agree that the rules that we set are good. Okay? They are sane. They are common sense. Okay? Now, the second question is, can we actually build a car that obeys this rule all times? And of course, it's not trivial, because maybe you decide something to do now and there is a butterfly effect and it will lead to a chain of events, and eventually you will not respond properly to some dangerous situation because of this initial thing that you did before. So we build the model, and part of the modeling choice is to build the model in a way that there will be an efficient procedure for guaranteeing that you will be safe according to the model at all times. So here we give 100% guarantee that the decision-making process is safe, okay? And the main mathematical tool is induction. Basically, I will explain the idea because it's really, really a simple idea. We formalize some notion of a safe distance. And then we say that a situation is dangerous if it is not safe both laterally and longitudinally. So longitudinally is this axis, laterally is this axis. Okay, so if you are now you are not safe longitudinally, but you are safe laterally. Now you are not safe laterally, but you are safe longitudinally. If you are not safe in both, then this is dangerous. Okay. We define blame time to be the first moment in which the situation becomes dangerous. And then the proper response depends on how what was broken last. So if the longitudinal distance was last to become non-safe, like in this scenario, lateral was not safe, longitudinal is safe. Now longitudinal is also non-safe, so longitudinal was last to become non-safe. Then the proper response is to break longitudinally. And if the lateral distance was last to become non-safe, you need to break laterally, meaning to stop the lateral movement. Now, from this, you can easily construct the notion of responsibility for an accident by proving that a collision can occur only if and only if one of the agents, or at least one of the agents, did not respond properly to the dangerous situation. And then this agent has responsibility for the accident. Okay? So I do not have a lot of time, so let me skip the details of the models.
So you assume that you can always break the situation? Let's say you're changing lane and there's a car that's following you.
Yeah, so one nice thing about, again, a design choice about our model is that it suffices to do it pairwise, and you're guaranteed to always, that you will always, it will always be possible to make the proper response. Okay? It's not trivial why, but we prove it, it is possible. Okay? But I wanted to, okay. I wanted to, maybe I will even, because I have maybe 5 or 6 more minutes. So I want to give you some highlights about the scalability and then show you some videos of our cars showing what we are doing differently than others. So some highlights about the scalability of our system. The first one is about mapping. So every autonomous vehicle solution relies on a high-definition map. High-definition maps are very expensive, and our idea is to have a high-definition map which is very cheap by 2 ideas. First, it is built by crowdsourcing, because Mobileye has many cars on the road that has its camera for just driving assist systems, not for autonomous driving. So we leverage all this information in order to build the map automatically and also update it in real time. The second aspect is that rather than building the high-definition map in 3D, we build it like in 1D. The natural curve of the drivable path is dense, but it's just 1D. And all the rest is sparse. And hence, it's orders of magnitude cheaper than vanilla high-definition maps. The second aspect is, as I said, camera-heavy solution. Cameras are affordable. And we add to this affordable radars and lidars rather than very expensive sensors. The third aspect is computing power. So we have our own chip, and also the design choice of the algorithms is built such that on a chip of around 5 to 10 watt, we can have all the computing power needed for the autonomous car. And this is orders of magnitude better than other solutions that rely on basically a supercomputer. The car is a supercomputer. And finally, we tune our system to be assertive so as not to block traffic. Otherwise, at least in Jerusalem, it is impossible to drive. And the reason we allow ourselves to do this is because we have this formal model of safety. So we have, even though we are driving assertively, we have guarantees on what exactly we provide in terms of safety. So a formal model helps us to go to the boundary of what is allowed, and this gives us assertive driving. So let me show you some of the aspects. This is a collection of sparse information for the map, and this is how the map looks like. So here we project the map on Google Images. So you can see that we have dense information of the drivable path and sparse information about 3D information for localization. This is a project we're doing with Nissan. We map all the highways in Japan using our solution. This one we already saw. OK, so I will show you some demonstration from a route that we are practicing in Jerusalem. What you see here is a merge. The main camera is on the top here. You see that there is heavy traffic, and we need to merge into this heavy traffic. Now, if we will be defensive, nobody will let us merge, in Jerusalem at least. OK? So we must push our way. You can see what happens on the side. The system, and there are elements here that involve machine learning, but the system must find the right moment to jump into the right spot, if you like, and merge into traffic. So we are crawling, and when there is an opportunity, hop, and we are fitted into traffic. So this type of driving is very, very complicated. Here is an example of changing lanes because you can see me here. I'm talking all the time, sorry. But you can see me here driving the car. There is a slow truck in front of us. And in order not to be stuck after this truck, we need to change lanes. So we push our way, wait to see that everything is safe, and then continue. So there is a negotiation here that we must do. If we will just go and do the lane change, it may be very dangerous because maybe the other drivers does not pay attention. So we must do something like pushing, seeing, and then if all clear, continuing. And the balance between doing it in an assertive way but at the same time safely is very delicate. Without a mathematical model, it's impossible to do this. I'm driving the car because I have a rule that because I'm writing the software after every major update of the software, I'm going myself to ride the car. That's another scenario. Let's see. This is a merge. We need to merge. There are 4 lanes that merge into 2. And part of the things of human-like driving is that you need to decide friend or foe about the other cars. So before you even start doing the merge, you need to map the other drivers and decide whether you take way or give way on every other agent. Okay, so these type of semantic decisions are very important to do. Now what we see, there is a tractor here on the highway. It doesn't supposed to be there, but it's Israel. So we need to overtake it, but there is heavy traffic. So we try and retreat back. Then after the 3rd try, we managed to do this. So again, it must be very, very assertive. Otherwise, we would be stuck behind this tractor forever. Here again, it's a more urbanic scene, and we need to change lane in order to take a left turn. And again, without being assertive, it's impossible to do this. things.
Are there routes pre-planned or?
Yeah, so the decision of how to go is inferred automatically, okay? But the destination is hard-coded,
Ah, okay.
okay? So how to build the route is done on the fly, but where to is hard-coded. Of course, in the future, this will be entered by the user. All right, so I will wrap up. So our goal is to make autonomous vehicles a real product and not just a science project. And the way to do this, or what we identified as the major obstacles, is safety and what exactly does safety means, and building a scalable solution that can scale to millions of cars. Thank you very much.